This is an example of how we can use a surface integral to calculate something other than maybe just the surface area. And we do that by overlaying some function on top of our surface. So here we've got a flat metal sheet that is given by this equation here, so our plane equation. And we've also got a density function that's given. And we know that if we integrate density, generally we get back to mass. So here, when we integrate that density function, we will get the mass of this sheet. So we're overlaying this density on top of our sheet, and therefore we're integrating that as a surface integral. So our general surface integral is the double integral over S of some function f of x, y, and z ds. And again, in order to get that mass, we want to integrate the density function. So the function that we're overlaying is this density rho of x, y, and z. In this case, that's going to be equal to x squared yz. And ds, we know, is calculated as a cross product of the two partials we get from our parametric form or our vector valued function that represents the surface. So I'll just write that out generally as the magnitude of Ru cross R sub v dA, where again u and v really depend on what kind of parameters we have for our particular surface. So let's go after that parametric form or our vector equation for our surface. So in this case, it's going to be r of x and y. We're given our surface directly as a function of z, so that allows us to create a quick parametric version or vector valued function here with x equal to x, y equal to y, and then z equal to the surface, 1 plus x plus 2y. So now we've created this vector equation for our surface. We now are going to find those partials. So I can take the partial of r with respect to x, and that's going to be 1, 0, 1. And we can take the partial of r with respect to y, and that's going to be 0, 1, and 2. And we know, of course, that we're supposed to take that cross product of those two vectors. So I've already done that, and the magnitude of that cross product is going to be equal to the square root of 6. So that piece is done. So now, in terms of setting up that integral for our mass, it's going to be equal to the double integral over the region D of our density function, x squared yz, times the cross product, or the magnitude of the cross product, which is root 6, dA. And now we just have to grab that region. In the problem, we're specified that we're going to be above a rectangular region here, where x is going to go from 0 to 4 and y goes from 0 to 2. So that makes our setup pretty straightforward in terms of that region D. We can integrate in whatever order we like. And I'll even bring out our square root 6 out in front of the double integral. And I'll maybe just do this as dy dx. So x went from 0 to 4, y went from 0 to 2. And there's only one other thing that we have to do, and we have to remember that our integrand itself also needs to follow the rules of the parametric equation. So z is in fact this surface here, and let's go ahead and sub that in. So 1 plus x plus 2y going in for z in our integrand. And now the mass is going to be equal to root 6, integral 0 to 4, integral 0 to 2 of x squared y times 1 plus x plus 2y dy dx. And as far as integrals go, that's a fairly straightforward problem to solve. We should be able to do this one by hand, but again, if we want to be able to use those computer algebra systems, we could do that as well. The final answer here will turn into about 696.74. And I encourage you to work through that on your own and verify that that's the value you get.